Okay. All right, everybody, we're going to get started. So I want to continue our discussion of lists, linked lists. And to get things rolling, I thought it would be kind of nice. I have my own set of notes on the subject as well. So I wanted to just emphasize how linked lists are preferable for certain problems if you're managing a collection of elements and when they're not so preferable. Okay. So just to emphasize what linked lists are all about, just review what we talked about on Wednesday. Remember, arrays are stored sequentially in memory. So if you're going to the UCLA-USC game next week, right, you try to call the ticket office. You have four of you. You want to all sit together. You want to all sit one next to the other. That's how elements in an array or a vector are stored in memory. Linked lists, not so much. Think of the case where you're at the stadium and you buy your tickets at the last minute and there are no blocks of 4 seats available. So what you have to do is everybody has to sit in other places, but just imagine you have to know there's too many people to remember in line, so what you ask is each person remember where the next person is sitting. Okay, so if everyone pays attention, I am a linked list, and I have a pointer to a node or an element in my collection. So you will be designated as the head of the list. You're sitting down in your seat at the game. Now, everyone pay attention, okay? After he is sitting there, you will be the next element of the list. Everyone see that? You see that? He will be the next element. Then she will be the next element after that. So everyone's job, who I point to, is to remember who is next, okay? And then she is next. Okay, you ready? So I know who the first element of the list is. You. Who's the next? He is. Okay, who's next? Who's next? Yes. Okay, fantastic. Do you see it's a lot easier to remember just one person in line versus everybody in line? So if I'm the linked list, all I know is I have a slip of paper telling me where the first person in line is. All of the nodes in the collection are speckled everywhere in the stadium in memory. So I don't know where everybody is. All I know is where the first person in line is. Each link in the chain is responsible for knowing the next link in the chain. Okay? So elements of a linked list are represented internally as nodes. Okay? This is what a node looks like in memory. There are 2 parts to the node. There's an int or a data portion. In my example, I'm using ints, but you can have linked lists of chars, just like you can have vectors of chars or bools or objects. Okay? So there's a data portion, and then there's a pointer portion. So the pointer is a pointer to another type of node. So there's a data portion which holds the data for the node, and a pointer to the next node in the list. So this is a pointer to another node object. Okay? So each node knows its information and where the next node is. Okay? So that's how nodes are represented in memory. And so we consider the next pointer as like a link. This links this node to the one next in the list. Okay? There are all different types of linked lists. Your book doesn't use these 2 examples. This is a very simple linked list called a linear linked list. And that's exactly the same type of linked list we did in our discussion, right? So you were the first node, who's the next? You just know who's after you in the collection and nobody else, okay? Now, you can see here, the linked list would actually just be this pointer pointing to the first node, and this node would be somewhere in memory pointing to that node, and so forth and so on. The last node points to null, because that signifies the end of the list. So in order to visit any element in the list, you have to start at the beginning and work your way to the node you desire. So you always have to start at the first element of the list and work your way down. So if I wanted to talk to the third element in the list, I say, okay, can you relay a message to who's next? Find out who's next. Okay, who's next? Okay, perfect. I wanted to talk to you. So do you see the process of trying to find something in the list is O of n? Because if the worst case scenario, I have to talk to, if there's a linked list of 4 nodes, then I have to go through 4 nodes to talk to her, right? So one other type of linked list is called a circular linked list. And the only difference is the last pointer, so the pointer for the next pointer for the last node points to the head. So this way, if you want to just use it like a Rolodex, where you just go around and around and around in order, you can go back to the beginning. So if you were kind of doing things over here, and you're saying, oh, I want to get back to the beginning, all I have to do is use my next pointer to get back to the beginning. So it's a little bit faster. So if you're somewhere in the end of the linked list and you want to access the beginning elements, you can use the next pointer of the last to get to the first.
Why can't we just use the node that starts the first point?
We could, but imagine that you are not the linked list. I'm the linked list. I know the first element. Suppose you're defining another function, which is not the linked list, or not a member function of linked list, and you still had to get access to that beginning element. And the only way you can do that, imagine you're passed in a pointer to this element, and you can't go backwards. So what I could do instead is just keep going forward till I hit the beginning. Or I can, if I'm at the end, for instance, then instead of having to start at the beginning and work my way over, I can just loop around. So it might be easier to loop around in some applications, but not in others. Okay? The book that you use, Big C++, presents what we call doubly linked lists. Now, doubly linked lists are different because you can go not only forward in the linked list, but backwards as well. So every node has a previous pointer, node pointer, and a next node pointer. So let's play the same game we did before, but let's pretend we're a doubly linked list. So I can ask you, who's next? OK. Who came before you? So you see the difference? I can go both directions. Whereas with a single linear linked list, I can only go one direction, from the beginning to the end. But now I can go both ways. So if I'm searching a record in a large collection, like a phone book, and I skip over one by accident, I'm like, oh, I forgot, I want the one before me now. It's a lot easier to go back one than going forward all the way through the list again until I get to the one before me. Right? So if I stop here, but I want this guy, instead of having to start at the beginning and work my way to the 2, I can just go backwards 1 and get the previous element in constant time. Okay, one operation, just access the previous pointer. Circular doubly linked list, the difference being the next of the last knows the head of the list, and the head previous knows the last. So again, this is like the Rolodex that can go both directions. You can go forward in the Rolodex or backwards in the Rolodex. Okay? So those are just 4 examples of linear linked lists. I'm just going to focus today on the linear linked list and show you some code for basic linked list operations so that you can see that linked lists are really good if you need to insert a lot of items into the list or remove items from the list. Because as we saw in our class on Wednesday, just putting an element into an array that at a specific position that's not the end is very difficult because we have to add a new element to the end of the vector and shift everybody over who's out of place by 1, right? Or if we remove somebody in the middle, we have to shift everybody over by 1 again. Or we have to remove everybody, including the one we want to remove, and just insert back the ones that we didn't want to remove. So it's a painful operation to insert in a vector or an array, or to remove in a vector or an array. But with linked list, insertion and removal is very simple, very easy, given if we know the position where we want to do this. Okay? So let's take a look at some cases. I'm sorry. Let's take a look at an example of what a node class would look like. My linked list class would be a friend because I want to access pointers of node objects directly without having to deal with get methods, for instance, like get next. I don't want to have to define a get next. There's a lot of overhead when I call functions. So I want to make my linear list class a friend of my node class. So it can manipulate node members directly, even if they're private members. Okay? I have a node constructor that takes in an int. And the parameter for the node constructor will be used to initialize the data member of my node. And notice in my private section, I have a pointer to the next node and a data member of type int. So this records the information that the node contains. And this is the pointer which gives me the next node in the singular linearly linked list. So as you see in my node constructor, I initialize the data member of the node I'm constructing with the value of data that is passed in. Okay? Now, again, I should also probably initialize next to null. That's a safe place for null to be, because right now next is a dangling pointer. It's a wild pointer. Just like any variable, you have to initialize it before you use it, whether it's in a class definition, a member function definition, or main or non-member function definition. Whenever you declare a variable, you need to initialize it before you use it. And with pointer variables, it's even more important because these variables hold addresses of memory. So if you try to use an uninitialized pointer variable, you may inadvertently access some address you shouldn't be accessing and doing something you shouldn't be doing. Pointers are very powerful. You can direct pointers to point to any area of memory, and everything that your system does lives in some area of memory. So you can inadvertently trigger, for example, the area of memory where the function is that reformats your hard drive, theoretically. You probably won't be able to do that, but the point is that you always want to make sure that you give your pointers safe initial values like null, so that if you try to use them before you give them a good pointee, you won't do any damage to the program or to the system you're working on. Okay? So the linear list class has a default constructor which builds an empty list and has a pointer to the node called head, so the beginning of the list. So I would have a pointer. If I'm a linear list object, if I were empty, my head node pointer would have value null. But if I had elements or nodes in my list, okay, all I would have as a member is a pointer to the first node in the list. And then I don't know any other pointers. I can access anybody else's pointers through him. Okay, so he can tell me who's next, and then I can talk to that person to find out who's next after that. And then I can ask you who's next. So in terms of memory occupation, a linked list is very light. It doesn't occupy much memory because all of the nodes are on the heap, and they're all speckled all over the place. So the only thing I need to move, if I moved a linear list over, all I'm moving is a node pointer, which is a very small variable. Okay, so they're very lightweight. Okay, so in my constructor for linear list, I just assigned head the value null. So that means that it's an empty list. Okay, and we detect that, we represent that graphically by putting two vertical bars. So null, like that. So it's always important to draw pictures of your linear linked list as you're doing code that manipulates them so that you understand the code that's adding an element to the list or removing an element from the list. Let me give you an example. If I want to create a node object, all I have to do is call the node constructor. So node pointer p gets new node. I pass in the value 4. What that does, remember there are two areas of memory, the stack and the heap. So we have the stack, which we've been dealing with in 10a. Anything we declare on the stack gets automatically deallocated when the block of code where that variable was declared finishes or returns, if it's a function. And then we have the heap, and this is the area of memory that we manage. We manage this memory because we tell the compiler or processor to allocate memory on the heap when we use the keyword new. And we tell the processor to deallocate that memory on the heap explicitly when we make a call to the delete operator on a pointer to that memory. So the new node 4 expression does the following. It makes a node object on the heap with value 4 and then returns a pointer to it. So that's what the right-hand side of the assignment does. You want to trap that pointer address, that address. So suppose that this node lives at address 100 on the heap. I want to trap that value using a node pointer. Okay, so I create a node pointer p variable on the stack, and its job is to capture the address returned by the new operator call. So the new operator call does two things. Makes an object on the heap, returns the address to that object. Because that object, that node object, is anonymous. It doesn't have a name. It's nameless. So how do I access that object? I need a pointer to it. Imagine you go to a party. You meet this very interesting person that no one else met. Okay, you just happen to be going for a glass of water. You meet someone really cool. You forget to ask them their name. They give you their phone number or address on a piece of paper. You write it down. The piece of paper is p, the pointer variable. Person leaves. You go home. You want to contact that person. The only way you can contact that person is to use the phone number or the address on that piece of paper to contact them. Okay, so if you don't capture that address, you meet somebody, you leave, there's no way for you or anybody else to contact that person because you tell somebody else, they don't know who that person is. So it's important to know where heap variables are because if you lose that pointer, 100, there's no way to deallocate this from memory, and that creates a condition called memory leak. Okay? So if I look at a node object, if p is a pointer to it, then I can refer to the node object without a name by using star p. I dereference the pointer p, right? So this node can be named or has an alias called star p. right? It's the node at address that P holds, right? So the node at address 100 on the heap. There it is. So this whole thing here is star P. This part of star P, the 4, is star P dot data. But I have to put parentheses before the star P, before the dot operator to emphasize that I want to dereference before I call the dot operator. This portion is the pointer next of star P, so I can call it star P dot next. Now, if you don't like having to remember the parentheses or the asterisk for the dereferencing of the pointer variable P, you can equivalently write this as P arrow data. And you can equivalently write this as P arrow next, which does exactly the same thing as the expression above it. Okay? So let's remember our pointer geography and our node geography. We have star P, okay? This is P arrow data, 4. And this pointer is P arrow next, which in this example will be null. So when you see the code on these slides, I want you to pay close attention to the pictures associated with them, because I'm going to animate the code as it comes down on the slide. Okay? So going back, star P, node star P gets new node 4. That makes this on the heap, returns the pointer. P traps the pointer is a local variable on the stack. P arrow next gets null, so this arrow points to null, a safe place for it to go. Now I created a node object. I want to do things like insert one into a linked list. So there are a couple of cases for insertion. You can either insert at the head, at the beginning, before you. I can put a node in before you. Or I can put in a node anywhere else. That's the other case. So take a look at the picture. I have my head node pointer. That's what the linear list holds. And then here's star head. Here's the first element of the list. There's you on the screen. Okay. So this is head arrow data. This is head arrow next, right? So what do? I do head gets the value of new node, passing in 5, and then head arrow next is null. So if head were empty, if the list were empty, this is how you would insert the first node into the list. Here's head arrow data. Here's head arrow next. Okay, so again, focus on the pictures and the code associated with it. So that's the first node in an empty list. That's how you do it. How do I insert a node at the beginning if there's already a node there? So now I inserted the first node in the list. I want to insert a new node to come before him in the list. Okay? So here's a new node. I make it called temp. Well, I have a pointer variable called temp. It gets the address of a new node with value 2. So this is the node I want to put at the beginning. So I make it. First thing I have to do is I have to make it. I have to give it the right data value, which is provided by the constructor call. This is also on the heap. Temp is a pointer to it. Now, if I want to make it the first element of the list, let me ask you a question. Study this picture carefully. Should I have head point to 2 and then have 2 point to 5? Is that a way to do it? Think about it. So I want to make head point to 2. So this guy will point to 2. And then I want head next to point to 5. Would this be a good way to do it? It's OK. Take a guess. If I had to ask, probability is that the answer is no. Now, why is that the case? If I move the head pointer to point to this, who's keeping track of where this person lives? This node lives. Remember the analogy of the party? You meet a great person at the party. You go home. You have the phone number or the address. You talk to your friend, and you erase the phone number and write somebody else's. You have now lost contact with the mystery person at the party. The mystery person. Gone. Because you took their phone number, you erased it. The only method of contact you had was on that piece of paper. You erased it, you wrote someone else's address on it. So what do? There's no way to contact that person. That node is just hanging out in memory, and nothing is going to be able to delete this or access this again. That's a situation called memory leak. Did you hear about memory leak in 10a? That's when you create something on the heap, but you lose all of the pointers to it. So there's no way to deallocate that memory, right? There's no way to free it up and say the system can use that memory for something else. OK, so maybe it's not good if we have only one way of contacting a given node, it's not good to move a pointer, that only pointer variable, to some other place. So if I have only one thing pointing to 5, I should not move this because I'll lose all contact with 5 in the heap. And that's bad. That's memory leak. That's bad. Whenever I want to move a pointer, it's really important to move, to have a backup pointer pointing to the same thing. So if I want to move head's pointer to point to 2, I should have some other pointer, some other way of accessing 5. So before you move a pointer, make sure there are at least 2 pointers pointing to that thing. Does that make sense? You need a backup. So if you were going to, let's go back to the situation at the party. You leave the party. You have the phone number of the mystery person. Your friend says, I have a cool person for you to talk to. Write their phone number down. OK, hold on. I need to store the old phone number on another piece of paper first. Then I can overwrite my phone number on the original piece of paper, right? So it's always good to have a backup record of your memory address before you move a pointer variable. So instead of moving head first and then this guy pointing to temp, let's do it in the reverse order. This is another blank piece of paper. Have this point to 5 first, like that. Temp next, this is temp next, gets the address of whatever head is pointing to. So temp next and head are sharing a pointee, right? Does that make sense? Temp next and head are sharing a pointee, this node. So now that I have 2 pointers pointing to the same pointee, I'm free to move head now because someone else is keeping an eye on number 5 here, right? So now I can assign head the value of temp, right? I want these 2 pointers to share this guy as a pointee. There you go. There was no memory leak, right? So I get a backup pointer for 5. This is just, oh, sorry. I get a backup pointer for 5. Oh, my clicker isn't working for a minute. Let's see. So I make the node I want to insert, get a backup pointer. So now 5 has 2 pointer variables keeping track of it. And then, oh, wait, this is, sorry. Backup pointer, oh, sorry. Backup pointer for 5. Sorry for those who are watching at home. I have 2 pieces of paper for the same address so that if I move this guy or overwrite this guy's address that it's storing, it's going to be OK. I won't lose the 5. So temp next gets head. So now temp next and head are pointing to the same node. And then head gets the value of temp. Now head and temp are pointing to the same node. And if you look at the list now, 2 is the first element and 5 is the second. So are there any questions about the insertion process and how crucially important it is, how uber important it is for you to draw pictures first before you code? Programming is 99% pictures and 1% code. A lot of times students are having problems with linked lists and data structures using pointers, and I see their code and I draw it out for them. And I say, this is what you're doing. I draw all these pictures, and then the arrows are going all over the place, and I'm getting memory leaks everywhere. And they're looking at it like, I didn't want to do that. So let me save you the frustration. Draw it out first like you see in the pictures, and then code it up with your knowledge of pointer geography. That's a very important lesson to learn in this class. It's really important for you to think in pictures. Okay? Draw the pictures. Don't be afraid. Draw them out. See how it works. Then code it up. Once you know once you know the idea, coding it is easy. It's 3 lines of code. That is O1. That's O of 1 insertion. 3 statements regardless of the size of the list. Inserting at the beginning is O of 1. Whereas in an array, you'd have to shift everybody over, right? But since everybody keeps track of the next, I only have to change my next, right? The head pointer needs to know where to go, and he needs to know who's after him. He is. Or before him. So you have to know who's after you. I have to tell you who's after you, and I have to make sure that now I know you're first. So I have to move 2 pointers instead of shifting n minus 1 elements over. A lot more efficient, right? A lot more efficient to insert in a linked list as opposed to a vector or array, because you would have to shift everybody from index 0 on over by 1. Okay? So that's inserting a node at the beginning of a linear list. What about inserting a node elsewhere? Suppose I know my position of where I want to insert. So I want to insert my 8 right before the 5. Okay? So what I do is I make my node with value 8. let's think about the idea. You tell me, where should I move this guy to point to 8 first? No, because memory leak. 5 is going to be missing. Right? It'll be lost in the heap forever. So instead, I have a spare piece of paper here. Why don't I have that point to 5, and then I can move the 2. So how would I do that with code? Temp arrow next gets the value of what? So I have current here, already given. Temp arrow next, that's this guy, points to whatever this is pointing to. What's this? Think of the name. What's this area of memory right here? I want this pointer. Who knows what the name of this pointer is? We said that this is temp arrow next, right? Hint, hint. So what's the name of this pointer? Current arrow next. So temp arrow next will get the value of current arrow next. They will both share the 5. Right? So since temp arrow next now holds what current arrow next is holding, I can move temp arrow next to point here. So I do temp arrow next gets the value of what node? Or I'm sorry, current arrow next. I want current arrow next to get the value of which node? Temp. So current arrow next in temp now point to the same node. And now I have current. So whoever goes to here knows that the next guy is 8, and 8 knows that the next guy is 5. Again, O of 1, three statements regardless of where you are in the list. That's constant time insertion. No shifting over, no O of n problems. It's O of 1, it's constant, it's fast. Even though my list can be a million elements, it's still fast. OK, now let's talk about removing a node. Now, if I want to remove the first node in the list, OK, I have a pointer to that element. Can I just do delete head? Or delete temp? Would I have a problem with that? If I delete this, who's keeping track of 5? Who? Nobody. So I have to keep track of 5 first. So I want head to be I want 5 to be the new head, right? So I can do head gets the value of whatever address this guy has. Who has this address? Temp next, right? So head gets the value of, head gets the value of, or head next. Either one. You can call it head next or temp next, right? So head gets the value of head next. So now head is pointing to the 5. So is temp next, right? So now that I have 2 pointers pointing to 5 and I want to get rid of this guy, it's OK. There's no memory leak. So I just delete temp, right? Again, constant time removal. O of 1. 3 statements, regardless of how big the list is. Insertion and removal are very localized. You don't have to worry about disturbing the entire collection. Just one little link in the chain. That's it. So let's try removing an interior node. Suppose I have a pointer to the previous element and the one I want to remove. Same idea. Just imagine previous is head, right? So previous next should get this guy. Because if I delete this first, I lose the 5. So previous next should get the value of current next. Right? That will do the following. Now I have 2 pointers holding 5's address. Now I can delete current, right? And no memory leak. Again, constant time operation. 2 statements regardless of where you are. There's no need to shift everything over by 1. So it's a very fast insertion, a very fast removal for linked lists. Now, if you wanted to loop through all the elements of your collection or traverse all of the elements or visit every element in your collection, starting at the beginning and moving your way down, what do you use for vectors and arrays? I can foresee 2 different options. What keeps track of position in an array? Anybody? How do you loop through an element? How do you print out all the elements of an array? You do. So if you have an array int a with values 1, 2, 4, say, right? What do? You do for, you use a for loop. Int what? I gets 0, I less than 3, I plus plus, and then you see out a bracket I, right? So I use an index to record position in an array, right? Or I could use pointers, using pointer arithmetic, right? I can have, I could do this also. I can have, if I have an array in memory, I can have a pointer pointing to this element at index 0. So if this is an int array A, I can do int pointer P. So I could do, let's do it this way. So I could do for int pointer P gets the value of A. That's the element at index 0, right? And I can do P not equal to null. Or actually, I can say P, I can say I guess what should I do? I could do address of P, or P not equal to A plus 3, right? Because this is A plus 3. This is A plus 2. This is A plus 1. This is A in terms of pointers, right? Did you see pointer arithmetic in 10a at all, or 10b? A little bit? So pointers can keep track of where you are in an array. So what I can do is I can loop through, and then I can do P++. And then I can do cout star P. Right? So I can have a pointer keeping track of where I am in a collection. But with the linked list, what can I use? I can use something called an iterator, which is, I could also use a node pointer to keep track of where I am, like a node pointer, say, called I or current. But remember, pointers are dangerous. And we don't want to give the user of our linked list too much flexibility as to where we can assign pointer variables to go. We don't want to be able to have pointers move all over the place. We want a way to take a pointer to a node and wrap it around an object. And the object is responsible for managing its member data, the pointer variable. So each iterator is an object, which is a generalized pointer. It's an object that really contains a pointer as a member. And its job is to record or keep track of a position in the linked list. Just like an integer variable, an index variable, or a pointer keeps track of position in an array or a vector. Okay? So iterators are objects that contain pointers as member variables. And their job, each iterator object keeps track of a position, just as a node pointer would. But it's safer than node pointers because you only restrict, because the iterator object is managing the pointer variable internally and encapsulates it. It hides the data from the user of the iterator. It prevents the user of your iterator from moving the pointer to point to places it shouldn't. So the movements of the pointer, like you can advance the pointer one place ahead or one place behind. But those are the limitations of the movement of the pointers. So the iterator object restricts movement of the pointers to very predictable small directions. You can have it advance one or go back one, but you won't make it point to random places in the array necessarily. Okay? So an iterator holds a pointer to a node, and that tells you the position of the iterator in the list. It also has a pointer to the list, the linked list, which created it. And because of this, we consider an iterator a quote-unquote generalized pointer. Okay? And because the iterator, like I said, encapsulates or manages the pointer internally, the user doesn't have direct access to the pointer, so the user can't corrupt the pointer and have it point to places it shouldn't. So it's a safe way of using pointers, iterator objects. Let me just show you what the code is, or what a picture of an iterator looks like. So instead of an index or a pointer, P, it's an object that contains a pointer, position. So think of the analogy. Int pointer P. Iterator that contains a node pointer. Okay? It also has a pointer to the list. The list only knows about the head element, right? The list only has a pointer to the head, but the iterator has a node pointer which keeps track of the position. The user can't access this directly. Okay? Only the only access that user has are given by public member functions of Iterator. So you can prevent a lot of movement of the pointer. I can have position, if I just had a node pointer without a wrapper around it, without an iterator around it, I could have it point here or over here. But when it's inside a nice safe object like an iterator, you can have it advance or go backwards maybe, but nothing really crazy. Okay? Very predictable movements. So here's an example of how I would define an iterator. You have a class called iterator. You want to make your list a friend of that class so that you can access the iterator's members directly. And then I have a constructor and other behaviors like advance one or go back one in the collection. And it keeps track of a position in the list, so a node pointer, and a pointer to the list that contains that node. So if you wanted to do something like so if you want to actually, once you define the iterator, if you want to create it, what you do is you have in your class for linked list or linear list, you define a begin and an end function. Have you seen these with the vector class at all? The vector class allows you to define an iterator as well to traverse elements of a vector. So you can do, if you had like vector int v, you could do v.begin, v.end. Okay? And what these particular iterators do signifies, this one returns an iterator object by value, which signifies the beginning of the list. This one gives you an iterator object by value that specifies the end of the list. Okay? And so inside of linear list, you have two functions which return iterators, one giving you the beginning, one giving you the end. And then here's the code for getting the beginning. You create an iterator object I, so that's like taking the place of the index. You set the position to the beginning of the list, the value of head, and the container is the object that calls this. So the linear list that calls this is a pointer to a linear list, the calling object. This is a linear list member function. And then I just return I. So this one will return a pointer to an iterator object which has a position pointer pointing to the head of the list. If I want to do one that returns the position after the end of the list, I just, instead of sending position to be head, I give it the value null. So this returns the iterator recording the position of the element after the end of the list. So this signifies that the current position is not an element of the list. So this is a way of, if you do like a for loop and use an iterator, this tells you where to stop. So when you're at the end position, you're no longer pointing to an element of your collection. Okay? So take a look at how we would advance an iterator. So if you wanted to move the iterator one to the right, you first have to make sure that its position pointer is not pointing to null, because you don't want to call position arrow next if position is null. So to do that, you can use a function called assert, which is in the cassert library, or you can do assert.h as well. So you call assert and then a condition. If this condition is false, position is null, and it terminates the program. So it doesn't let you continue. Okay, so what you do is you just set position the value of position arrow next inside of a member function of iterator. Okay, so that's how you advance an iterator. It's also important for you to compare two iterators to see if they both represent the same position. So you can have two different iterator objects which have the same memory location stored in its position members. Okay? So you want to have different iterator objects which share the same pointee to be considered equal. So you can overload the equals operator if you want to do that. So this returns true if the calling object's position is the same as the position of I, which is an argument passed in. So this allows two different iterators that have the same position, the same memory address held by their position members to be equal. So if you want to get the value of a node, if you want to do star p, like you're doing here, if you want to get the value of the pointee or the value of the node, you can do return position arrow data, assuming that position is not null again. Okay? So that's how you get the for. You just, inside of the member definition of iterator, you just return position arrow data. Now, if you want to traverse the list, so pretend this is the name of a linear list, okay? And this is an iterator called I, an iterator object. So first of all, I can create a for loop just like I did here. Look at the similarities between what we did here and what we're doing here. The only difference is there's an object wrapped around the pointer. There's some object I that's holding this pointer and keeping track of it. That's all. So for iterator I gets the value of list.begin. List.begin gives me an iterator that you see here. So I will look like this. Its position will point to the head node, and its container will be pointing to list. Okay? So that's the initialization of the for loop. Then you keep going. While I does not equal list.end, print out the value of the data member of that node that it's pointing to. So this is like star p. In fact, you can overload the star operator instead of doing i.get, if that's more natural. Okay? So I print out the value at that particular node. So initially, this will print out the 3. I.get will give me 3. So then I print that out. And then the increment, I.next. So that'll move I to point to the next node, the one ahead of it. So you can see that the movements of the pointer position are controlled. You can either advance it one or make it go back one. So there you go. I.next does this. And now I is pointing to the second node. I print out I.get. I print out the 2. Advance by calling I.next. And I print out the 4. And then after this, I.next will be called again. And I will be pointing to the null. And that will make this false. Because when I is pointing to the null, when the position of I is null, this will be true. And the not would make it false. So that'll cut the for loop. So list.end returns the position after 4. So when I moves past 4, it will be the same value as list.end, according to our overloaded equality operator. Now, one question is, why did I not do I not equals list.end? Because I didn't define not equals for operator. I didn't define that operator for the iterator class. So if I wanted to use not equals, I'd have to overload that operator. Have you done operator overloading yet in 10b? Okay, so you understand that I'm only limited to using double equals because I haven't defined not equals, right? But this is so simple. It's just this, but with an object around the p. That's it. So it's a little bit fancier, but a little bit safer, okay? So with that in mind, I wanted to show you some of the standard linked list operations. So the name STL is actually now a misnomer, just to warn you. Your textbook refers to the list class as an STL class, standard template library class. But we don't say standard template library anymore. So I just wanted to qualify that in case Professor DeSalvo gets, like, why are you teaching them that it's STL? It's not. It used to be called STL until they standardized the language. Now they call them the C standard lists. Okay? They're templated classes. So just like vectors, you can specify what type of data your containers hold. So you can make a linked list of ints or doubles or chars, just like you make a vector of ints, doubles, or chars, respectively. The same way. Okay, so when I refer to them as STL linked lists, I just mean the standard C++ linked list library. Okay? So I just wanted to qualify that before we continue. But I use STL here as a matter of convenience because I want you to think a standard library that's actually templated, so you can create multiple versions of lists classes. Lists that hold ints, lists that hold doubles, etc. Just like for vectors. So remember the pros and cons of linked lists? Really good running time for insertion or removal. Horrible access time, because you have to start at the beginning of the list like we did. Remember in the example at the beginning? If I want the 4th element, who's next? Do you remember? Who's next? Who's next? How long it took me to get to you? For an array, I just say A bracket 3. Boom, there you are. Constant time access. But for vectors, same thing. Constant time access, A bracket 3. But for linked lists, it's expensive to find a position in the list. But it's really nice. It's very cheap to do insertion and removal. So if you do a lot of insertion removals, this is the data structure you want. Constant time. It's the best running time ever. For arrays, the pros are, like I said, very efficient element access for random access. If you want to access a random element in a collection for an array or vector, it's constant runtime. You just have to know the value of the index. But you can't resize arrays, even though you can resize vectors. And when you insert or remove in an array or vector, it's expensive. It's O of n, right? Because you have to do that stupid shifting over each time by one element when you insert or when you remove, so that everything's still contiguous in memory, right? If you take something out in the middle, you got to move everything over to right over the gap, right? So if you want to use the list class, what you can do is include the C++ library called list. That's using the STL linked list, or the C++ standard list, which is a templated class. Okay? So just if you want to create a list that holds int elements, just like if you want to create a vector that holds int elements, it's the same thing. The class name, list, the type of value you want to contain, ints, and then the name of the list is L, or whatever you want to call it. Okay? So this creates an empty list with no ints inside, no nodes inside. Okay? Now, look at the picture. So this is the result of calling pushback twice. So just like vectors have a pushback function, so does the list class. And what it does is it adds an element to the end of the list. So if I do list int L, and then I do L.pushback2, you'll just see the 2 here, and then null for both the previous and the next. Then I do L.pushback7, and it puts the 7 right after the 2. Okay? So now 2's next points to 7, 7's previous points to 2, 7's next points to null. Okay? So that's what happens when you call pushback. Now, if you want to access elements of the list, you can't use the bracket operator like you do for vectors or arrays. Okay? So what you need to do is traverse your collection using an iterator. That was the thing we were talking about before, the generalized pointer, right? So what we have to do is define an iterator object. So what is a little bit technically crazy is that the syntax is a little annoying. You have to do list, what type of list, list of ints, colon, iterator, the name of the iterator, so you can call it I or position or whatever, and it gets the value of the list.begin, just like before in the code I showed you before. So this gives you an iterator to the head of the list, as the picture suggests. This is an iterator object. Its position pointer points to 2, which is the value of L's node pointer. Okay? So now I initialize my iterator to point to the head of the list. And if I want to move it, I can use the ++ operator, just like if I were advancing an index. So the ++ actually works for iterators as well, which is very convenient notation. So when you do your for loops, they're going to look very similar to for loops that depend on indices. Okay, so if you want to move to the next guy, if you want position to point to 7, you do position ++. And that advances the pointer 1 ahead with the same object, POS. Okay? Okay, so then if you want to go backwards, you can do --, just like you do for int I. So if you want to go back to the 2, you can do position --. So the decrement operator is also defined. Now, if you have a choice between pre or post-fixed, you can actually do the prefix. And I would recommend doing the prefix over the postfix. So if you want to advance the pointer, do ++ position. Or if you want to decrement the position, you do --, position, because it's actually more efficient. The postfix actually clones an iterator, and that requires processor time and memory. So it's actually better to do a prefix because you actually change the calling object, if you will. Okay? So that's how you increment and decrement. You can access an element using the star, just like you do for pointers. It's a generalized pointer, right? So if I want to access the first element's value, I can do star and then the name of the iterator. So operator star is overloaded for iterators. It prints out, if I printed it out, well, first I use it to set the value to 5. So before it was value 2, but I can do star POS gets 5. It changes the data value to 5 for this iterator, POS. And then I can just print out its value by doing cout star POS, and that prints out the 5. So whatever data that position is pointing to. Okay? So again, they're just like pointers, notationally speaking. In fact, they are just nice, safe classes that wrap around pointers. So the objects hold the pointers. You don't get direct access to the pointer. That's the only difference. Okay? And then if you want to insert before a position, you need to know where the node is of the position of the node is where you want to insert before. So if I want to insert before the 5, I do L.insert position 3. So this puts a 3 before position. So the 3 goes before the 5. Okay? So when you pass in an iterator to insert, you have to pass in the position after. So it'll insert before that position. So the 3 will come before the 5, and then position still points to the 5. Okay? Now, if you want to remove, or if you want to insert at the end of the list, remember you have to insert before the node after the last element. So you have to insert before L.end. Since L.end is the element after the last element, you want to insert before that. So that would be the argument for insert if you want to tack on 1 at the end. Or you can just do L.pushback, right? Which is a lot easier. But you want to insert before the last element. This is L.end. So I want to insert before, or it was, I guess it was here initially, right? So if you want to insert the 8 at the end, you just pass this iterator into the insert function, and then the 8 will go before the end. It'll put it between the 7 and the null. Okay? If you want to remove the value at position, you do erase. So you can do L.erase position. Remember, position here was pointing at the 5. When I do L.erase position, it removes the 5, fixes the list up so that it's still a linked list, and now position points to the next element. Okay? So that's what erase does. You can use erase to remove an element from the linked list using the C++ standard list library. And that's all we have for today. So I hope you enjoyed our lecture and have a great weekend. And Professor DeSalvo will see you on Monday. So have a great weekend. Thank you.